So in section 7.4 for calculus 2, we are going to be talking about the area and the arc length of polar coordinates. So thinking about the area and the arc length, let's start with the arc length. So with the arc length, we know our parametric equation. And our polar is very similar because polar is also done in terms of x, in terms of y. Instead of done in terms of t, though, as a parametric, we take it with respect to theta. So here's our polar. All we're doing is substituting in d theta instead of dt. So we're taking the derivative of x with respect to theta and the derivative of y with respect to theta. We'll kind of think about a couple other things here for the formula. So r is equal to the function with theta, with respect to theta, so r primed is equal to the function derivative with respect to theta. And also remember that x is equal to r cosine of theta and y is equal to r sine of theta. So if we take the derivative, we already talked about that derivative right there, right? That's going to be our dx d theta, and then that's going to be our dy d theta. If we square them out and add together like terms, we'll find out that we have a cosine squared plus a sine squared and a cosine squared plus a sine squared, which are just both 1. So we end up having the derivative of the function squared plus the function squared. And remember, the function is r, so it's really r squared plus the derivative with respect to theta of r squared. So just kind of a nice way of kind of thinking about how you get that and being able to maybe even recreate them without too much memorization. Very similar to what we did with our parametric equations. So now it's always best if we graph these, and we have a cardioid here, and we want to find the exact length of our cardioid of r equaling 2 plus 2 cosine theta. Well, if we look at this graph, it's going to take me from 0 to pi to graph half of it, and then from pi to 2 pi. And we notice that the top half is equal to the bottom half. So we could find our arc length by doubling our area and going from 0 to pi. A little bit nicer sometimes when we can do stuff like that. Now we're going to do the square root, and we're doing the square root of our r squared, so that's 2 plus 2 cosine theta squared plus, we need r primed here. The derivative of 2 is 0, and the derivative of 2 cosine theta is negative 2 sine theta. So then we're going to have negative 2 sine theta squared d theta. So here's what we're doing, our formula for arc length. And now really it's just going to be a matter of kind of manipulating these algebraically to get what we want to get going on. Something maybe we could take the square root of, because they want the exact arc length, which means I don't just want to throw this into a graphing calculator and find the derivative of that, the integral of that, because that won't be pretty. So we're going to have 4 plus, if I square this out, 8 cosine theta plus 4 cosine squared theta, and then if I square the second part of it out, that's going to be 4 sine squared theta. Well, here, if I factor out that 4, I have cosine squared plus sine squared, which is 1. So I end up with 2, the integral from 0 to pi of 8 plus 8 cosine of theta d theta, and that's underneath the square root. And I want to be able to take the square root of that thing, which right now I can't. So I'm going to think about how might I change that cosine of theta to be a square. And so we know the cosine of 2x is equal to 2 cosine squared of x minus 1. So if we want to replace the 2x with a theta, right? So 2x with a theta, then we would have 2 cosine, and it's 2x, so it's just a single theta, so it would have to be theta divided by 2 minus 1. So let's replace that right here. So 2 cosine squared of theta squared minus 1. And remember, that's going to be distributed by an 8. So we're going to have 8 plus 16 cosine squared of theta divided by 2 minus 8. And my 8s are going to cancel out. And now I'm going to have a square root over that. I'll be able to take the square root of that. So I'm always thinking kind of ahead oh, I have a square root. I want something I can take the square root of so I can do its integral. So I just manipulate algebraically until I kind of get what I want. And that's how I know kind of what I want to change around. Now, let's put it all together here. Let's take the square root of that. So our arc length is equal to 2, 0 to pi. Square root of that's going to be 4 cosine of theta divided by 2 d theta. So now let's take our integral here. We'll multiply the 4 times the 2 and we'll have 8. And the cosine of theta divided by 2 is 2 sine of theta divided by 2. And that's going from 0 to pi. So we should be ready to plug in and just be about done with our arc length here. So our arc length is equal to 16 times the sine of pi over 2 minus the sine of 0. So the sine of 0 is 0. The sine of pi over 2 is 1. So that's equal to 16. Well, that turned out to be a really nice arc length. The next problem says set up an integral and then use your calculator to find the arc length of the polar curve of r equaling 2 over theta over the interval from pi to 2 pi. Round your answer to the nearest thousands. So we have our r is equaling 2 divided by theta. So r primed, let's see if we think about this as 2 of theta to the negative 1. That's going to give us negative 2 theta to the negative 2 or over theta squared. So our arc length is equaling from pi to 2 pi, the square root of r squared. So that's going to be 2 theta squared plus r prime squared, which is going to be negative 2 over theta squared squared. And you could square those out, or you could put them in your calculator just like that, which is what I did. And our arc length is approximately equal to 1.424. So we like sometimes when we can just throw those in a calculator. So those were the arc length. Let's take a look now at area problems. So let's look at the area of the polar curve. So the area of the polar curve, we're really thinking about this as area of a sector. And our formula for area of a sector is 1/2 theta r squared. Okay. Or that's the opening of that angle. So there's that area of a sector formula. So if I think about that, how far is that angle opening, right? We're looking at one of these little guys right here. That angle and that arc length of that angle, they're the same, and that's delta theta, right? The difference of how that's opening each time. And then the distance going out, that's my radius at any point in time, or my f of theta. So that's kind of where my formula comes from. We're adding up all of those triangles. So we have 1/2 delta theta times f of theta squared, r squared. So delta theta is really d theta. So we have 1/2 f of theta squared d theta, or we might even think about a little bit easier as 1/2 r squared d theta. And then again, if I have the area between two curves that I'm doing, I have my 1/2 r big R squared minus little r squared. Okay, so thinking that's my formula, now let's go ahead and do some examples. It says find the area of the region enclosed by one loop of the polar curve r equals cosine of 2 theta. So again, let's graph that polar curve. And if you don't remember what it looks like, throw it in your Desmos calculator. The 2 theta is making it have 4 petals, so to speak. Okay, this is, and I just want 1 petal. Well, to get all 4 petals, I have to go from 0 to 2 pi. You could maybe think about what it takes to get 1 petal, but if we did the whole thing and we divided, since we know each petal is 4, then if we divide by 4, we would have our area. So area is equal to 1/2 times 1/4. The 1/2 comes from my formula. 1/2. 1/4 comes from the fact that I had 4 petals and I only want the area of 1, right? So that's the 1/4. We're going to go from 0 to 2 pi, and it's going to be our r squared, so cosine of 2 theta squared d theta. So there's my formula that we're going to use. Let's go ahead and do a little algebra here. So 1/8, I have cosine squared, right? And we're going to change our cosine squared into a regular cosine so we can integrate that because I don't have a square root or anything. So that's going to be 1 plus cosine of 2 theta, and I already have a 2 theta, so that's 4 theta. So there's my, and it's 1/2 times that, right? So it's 1/2 cosine of 2 theta. That's my formula for cosine squared of theta. So I need a 1/2 out in front. And then that's d theta. So I have 1/16, 0 to 2 pi of 1 plus cosine of 4 theta d theta. Now we should be ready to integrate that. And if I integrate that, I'm going to have 1/16. The integral of 1 is going to be theta, plus the integral of cosine of 4 theta is 1/4 cosine, 1/4 sine. I have to integrate that. Sine of 4 theta from 0 to 2 pi. So we'll plug in now, and my area is going to equal 1/16 times 2 pi plus 1/4 sine of 8 pi minus 0 plus 1/4 sine of 0. Well, that's 0, that's 0. Sine of 8 pi, that just goes around back to 0, so that's 0. So we end up with pi over 8. Now, I'm not going to do the second way, but there is another way. I'm just going to set it up. So just to set it up, you could do the integration. If I only wanted to do one loop, so instead of dividing it by 4. So thinking about one loop. So let's think about this one loop right here, right? Well, this is going to be from pi over 4 negative to pi over 4 positive. And you could practice with your Desmos, kind of graphing that, or however you would want to do that. So my area would equal 1/2 the integral of negative pi over 4 to pi over 4 of cosine of 2 theta squared d theta. And then the rest of the math is pretty much the same that we just did before, but now I just didn't have to divide it by so much. Let's look at our next example. Find the area of the shaded region of the spiral, and they're giving you the formula. The spiral is r is equal to 2 theta, and again, put it in your Desmos calculator, but you can almost think I'm going around in my circle, right? So I'm going to go from 0 to 2 pi to complete that. So that's my bounds. So my area is 1/2 the integral from 0 to 2 pi of r squared, so the square root of theta squared d theta. So this one becomes fairly simple here. I end up with 1/2 the integral from 0 to 2 pi of theta d theta. Now I can integrate that, and that's going to give me 1/2 times 1/2 theta squared from 0 to 2 pi, or 1/4 times 2 pi squared minus 0 squared. So that should be pi squared. There's my area. In the next example, it says graph the curve and find the area that is enclosed by 4 plus 3 sine of theta. So let's go ahead and start by graphing that. I'm just kind of using my Desmos here. This is going to be 7 and negative 1. And my graph is going to look like a cardioid. It just kind of shifted it around a little bit. And again, to do that, my bounds are going to be 0 to 2 pi. So my area is equal to 1/2 0 to 2 pi of 4 plus sine of theta squared d theta. So we're going to have to square that out and get 16 plus, I forgot my 3 on my sign. I knew I was missing something there. So we have 16 plus 24 sine of theta plus 9 sine squared of theta. Let's replace that sine squared of theta here with, remember that's 1/2 1 minus cosine of 2 theta. So we're going to have 1/2 the integral from 0 to 2 pi of 16 plus 24 plus 9 times 1/2 times 1 minus cosine of 2 theta. Oh, I forgot all of that with my 24, didn't I? So I need my sine of theta here. There we go. So if we split this up, it might be a little bit easier. I'm going to divide them by half as I split them up. So 0 to 2 pi of 8 d theta plus 0 to 2 pi of 12 sine of theta d theta. And then here I'm going to have 9 over 4. I'll just pull that out. 0 to 2 pi of 1 minus cosine of 2 theta d theta. So let's go ahead and do our integration. We're going to have 8 theta plus, how about a negative 12 cosine of theta plus 9/4 theta minus, if I do this, I'm going to have a 2 out in front, so I'm going to have 9/8 sine of 2 theta. So there should be my integration, and all of those are from 0 to 2 pi. So let's go ahead and plug in 2 pi. So I'm going to have 8 times 2 pi minus 12 times the cosine of 2 pi plus 9/4 times 2 pi minus 9/8 times the sine of 4 pi. So that's plugging in my 2 pi. Now, plugging in my 0, I'm going to have 0 minus 12 cosine of 0 plus 0, and sine of 0 is 0, so plus another 0. So we have 16 pi. This is 1, so minus 12. Here it's plus 9 over 2 pi. That's 0, 0, and then I have another plus 12. So my 12s cancel out. So I have 16 pi plus 9 over 2. So if I did this over 2, that's 32 pi over 2. And if I add those, I'm going to have 41 over 2 pi. In our next example, number 4, it says find the area of one loop of the polar curve of 4 sine of 4 theta. So if we remember the graph of this, or if you want to put this in your Desmos, the 4, since it's even, it's going to double all those. So I'm going to have 8 petals, which means I'm going to have 2, and sine means that the petals are inside, not on the axis. So they're inside the quadrants. So there's my 8 petals. They should all be even, but I have 8 loops. And remember, I only want one loop of this. So we're going from 0 to 2 pi to do the whole thing. So I could be 1/8 for one loop, right? So that gives me one loop. So 1/8 times 1/2, the integral from 0 to 2 pi of 4 sine of 4 theta squared d theta. Let's square that. And if I square that, I end up with 16 sine of 4 theta, and my 16s are going to cancel out, so I have 0 to 2 pi of sine squared of 4 theta, d theta. So let's switch our sine squared out, and let's make that be 1/2 times 1 minus cosine of doubling that angle of 8 theta d theta. Now we can go ahead and integrate that, so it's 1/2 times theta minus 1/16 sine of 8 theta from 0 to 2 pi. If we plug in then, our area is equal to, if I plug in 2 pi and I have 1/2, that's going to give me pi. And if I plug in 2 pi, that's going to give me, into sine, that's going to give me 0. And if I plug in 0, I'm going to get 0. So my answer is just pi. So there's my area. And I'm going to end this video here and pick up the last couple of questions on a short little video with the area between two different curves. See you in the next video.